Hello, everyone. My name is Stacy. I represent Vettabase Marketing. Welcome to our webinar, Everything You Probably Never Wanted to Know About NULLs in PostgreSQL. Please be aware that we'll share the webinar materials with you via email soon after the webinar is over. You can ask questions during the webinar using the corresponding tab, and the speaker will answer them after the webinar. Our today's speaker is Chris Travers, Senior PostgreSQL Consultant. Hello, Chris. Are you ready to take our virtual stage?
Thank you, Stacy, and thank you, everybody, for coming to my presentation, Everything You Never Probably Wanted to Know About Null. Now, I assume that probably most people here have at some point been bitten by null behavior. And one of the interesting things about this presentation is that we're going to talk about why nulls don't make sense, where and when to use them and why not to use them in many cases. And we'll be digging into the history of this so you can actually understand why nulls are as much of a mess as they are. I think that'll make a little more sense as I introduce myself, but I want to give you kind of the problem statement before we start. If you try to spend your time figuring out how nulls make sense, eventually you will hit enough corner cases that will make you start to realize that they really don't. So, about me, I've worked with Postgres for 25 years. But just as important as that, my formal education is mostly in history. And this will come in really handy as we talk about this. My father's formal education is very much in mathematics, and that also comes in handy. And so basically, I'm looking at this both in terms of the mathematics and the history of databases, as well as programming languages in general, and how we end up in this situation here, where nulls exist, where they don't make sense, and where where we end up getting bitten by null behavior all the time. Now, as I get started here, my slides are mostly here to explain points. I'm not really outlining the talk on the slide so much. So I want to start by talking about databases as inferential systems. Now, when Cod proposed the relational model of databases, he was very clear about the idea that the relational model would provide an ability to draw inferences from our data, and that this would be specific to the mathematics of the database model itself. In other words, we can treat the database as a math engine which we can process data with, and it can give us new facts that are implied by what we have stored in our database. So this is the promise of relational algebra, and it's based on the idea that we have a database that constitutes a set of corresponding facts or relations. And so basically, our relational databases start off with this very lofty goal of being very clear math engines that are going to simply make sense and deliver us the answers that we need based on what we've stored. So in the mathematics of databases, we have exactly two kinds of nulls, neither of which are the nulls we're going to talk about today, although they do overlap. The first is a null set, which is a set with no members. A null set is basically like a table with no rows. We don't usually find this very interesting, but it is a mathematic null in our database, right? And so this is the starting point. The second is the null tuple. The null tuple is like a row with no columns. It's also not very interesting until we actually get into corner cases of null behavior, which we will in a bit. But it is also a mathematically defined null. What we call nulls, however, in databases are neither of these things. And we didn't get it from mathematics. Instead, we had to deal with the fact that the lofty goals of a mathematical engine collided with demands from the real world. And so we borrowed an idea from programming languages, and we get to thank this guy, Sir Charles Anthony Hoare. In 1965, Sir Anthony Hoare was working on developing Algol 65, and they were trying to build Fortran compatibility into it with the idea that this would allow more people to leverage both languages together. And one of the things they came up with to try to square the issues of how the data structures were different was to allow something called a null reference. I assume most people here are familiar with that. That just means a reference that is pointing to a value that represents nothing. So basically, null references have plagued the programming industry quite a lot. For people who have worked with Rust or some other languages, I think Golang does something similar. There's a movement away from null in many of null references in many of these cases towards like things like maybe, this may be defined or maybe not, and then that way you can confine your cases where you actually don't know if you have data to a smaller number of cases. But at any rate, in the database world, we found that there were cases we might not have data, and so we just simply borrowed this idea from Algol 65 and similar languages. The problem is that this is not a well-defined concept, right? It's not a well-defined mathematical concept. Instead, it's an implementation detail for dealing with the real world. So we can't really think about null as a concept in databases. Instead, we have to understand that it is nothing more than an implementation detail for dealing with missing information. This is critically important for understanding the rest of this presentation, because if we try to think about what does a null mean, it doesn't mean anything. It can mean all kinds of stuff or not at all, and it's basically an implementation detail that's been thrown into many different use cases in databases without really a coherent plan on how it all fits together. So with this being said, I guess the first thing to point out is that we probably all have dealt with the three-value logic. Null equals anything is null, right? So if you have null equals true, null equals false. So for three-value logic, we've all been bit by this at some point. If you have null equals anything, that's null. There's a difference between like true is null, true is true, null is true. Interestingly enough, is an interesting case, because the is operator, when dealing with Boolean, never returns a null. Null is true returns false. That would not work if we strictly looked at nulls as unknown. So most of us have been bit by three-value logic, right? As I mentioned, equals can return null if one side is null. Is does not return null. And so null is not null is false. True is not null is true. This does not work if we think about null as simply meaning unknown. And so the basic thing is the is operator exists in part to differentiate values that include nulls, right? We also see is distinct from for non-binary types, but this is the key thing. The other large beginner mistake is perhaps not choosing the right operator. As I said, is and is not never returns null, but it's only for Boolean. Is distinct from and is not distinct from do the same thing for non-Boolean values. Comparisons return null when one side is null. So, null is greater than infinity returns null, which is, again, doesn't make sense. except to treat this as, you know, a set of very strict rules relating to an implementation detail that's sort of organically grown up around some of the problems of handling missing information. Now let's talk about some advanced fun. Row types and null. I assume many people here have not tried row types as null, right? Row types would be like composite types, or cases where you have like a row which has multiple columns and you want to see whether that row is null. Now, the cases I'm looking at here are all from Postgres. I actually have not tried some of these in other databases, and given how much I often have to test this behavior to make sure I understand it, I would assume that only those things specified by the standard may be portable. So row types are null if and only if every column is null. If there is one non-null column, then the row type is not null. Arrays, however, are not null even if every member of the array is null. So if you have an array and it's actually and it is specified as an array, then it is not null. But row types can be null if all fields are null, and this is actually quite useful, at least in the case of Postgres, and I would assume other databases handle that similarly because that is specified in the SQL standard. We're going to talk a little bit about is null values and not null fields, and we're also going to talk about one special case here, which I don't have in my slides, but I want to actually mention here. And that is that if you have a row with 0 columns, so this is a null tuple. A null tuple evaluates to, if you have the null tuple is null, that evaluates to true. Because it doesn't have a not null field in it. But if you do a null tuple is not null, you also get true. It is the only value I know of, at least in Postgres, that evaluates both as null and as not null. So this is an interesting corner case. It's something I discovered by accident, and it's something which can bite you if you're like cutting corners on some of your tests. So the next issue is here. This also gets into like implementation details problems. Suppose I create a custom composite type, right? And then I create a table which accepts a column of that type and specifies not null. Now suppose I insert into it a row of only nulls. Interestingly enough, at least Postgres allows this to happen. I assume most databases do also, and I'll discuss why in just a moment. If I then alter the table and I add a not null constraint, that not null constraint will fail. I will not be able to add it. The reason for this is there's a big difference between a not null designation on a column and a check constraint, and that a check constraint actually executes and checks an expression, while the not null constraint on a column simply checks to see if we are storing a null in that column. In other words, if we store a value that evaluates as is null, then we can still do that because it is a value rather than a null. So not null only checks for basically null values. This is like null references. It does not check for values that we have decided to treat as null. And this makes sense because usually we have very abbreviated checks in this path because this is a performance critical path. We do not want to be engaging in heavier checks on every row we insert because that would kill performance. So this is a really good example of implementation details being exposed by the fact that nulls don't make any sense. I'm not quite sure what equivalent behavior would be in MySQL and a couple of other databases, but this is a really good example in Postgres. The next thing we're going to talk about here are anti-joins. Now, for those of you who don't know what an anti-join is, it is basically similar to like a not-in query, right? We want the rows from one relation where a join condition to another relation is not met. If we do an anti-join this way, right? Select star from A where B some val not in, select some val from B. Then if there is a null in some val in the some val field in B, then we will return 0 nulls from this attempt at an anti-join, simply because null in a not in never matches, and therefore we cannot therefore we do not get a result out, right? So in general, if you're trying to do a anti-join, not in is a general bad practice, largely because you will find yourself in these situations where anti-joins fail because there is a null somewhere, and consequently, instead of getting results that you expect, you simply get nothing back. So a minimal fix to this is to add a where clause in the not in subquery, and to simply say, you know, where some val is not null. And now suddenly we have something that will always sort of work. There are some problems with it, though. First is it's error prone. If you go ahead and, you know, sort of accept this sort of thing in your coding standards, you will likely run into situations where somebody has missed this code review, the where clause is not there, and then suddenly something fails and everybody is wondering why. So the minimal fix I don't generally recommend. It can be useful some cases, but it's not something that I would typically do. The more standard fix is to suggest to people that they use a exists, not exists subquery instead. And what the not exist query does is it effectively runs, it effectively returns the rows where this join condition is not met. This is closer to what the advice normally is, but and some databases I think can optimize it pretty well. The larger problem is that because exists and not exists is are very general tools, and you can put just about anything you want in the subquery, that the planner is limited in terms of what it can assume about the input and output of the query, right? And as a result, my own experience is that despite the fact that people usually say this performs better than in and not in, my experience is that if it performs better, it's only a little bit, and it can sometimes perform quite a bit worse. So I have found this approach to be performance problematic. It can be used, but there is a better way, at least on databases where you can evaluate a row as null. Sorry, it looks like the apparently there's an orthographic problem here. It should be select a dot star from A left join B using some val where B is null. What we do here, which is in my estimation the best way of doing anti-joins, is we set it up as basically a left join, and then we evaluate the left side tuple as null. In other words, we want the rows that come out of the join where the join was not matched. And then we only want the columns from table A. And the nice thing about this is that we can do something like a hash join or a merge join or whatever our standard join strategies are, and we can just return the table tuples from it. Now, in theory, databases which have really good optimizers for things like not exist queries can recognize those not exist queries which reduce to this form and effectively turn them into it. But for cases where planners have not been optimized for that, then you're kind of stuck with going this route, which is basically you do a left join and you throw out anything where the join is matched. So that's some basic points about actually a really cool use case for nulls, which leverages sort of the standard, the SQL standard rules relating to when a row is null. But again, this is standardized behavior. It's not necessarily something which is that is thought about in terms of a consistent concept of what null represents. If you get one thing from this, one thing I've said many, many times is that null doesn't represent anything. In fact, it just simply represents no data here, which is exactly what a null reference represents in your favorite programming language. So at this point, I want to just take a few minutes and a number of minutes, and I want to talk about best practices, and then we can get into questions and answers. Because nulls are basically an equivalent idea to null references in programming languages, there are a number of problems with using them. I know that in many cases they are unavoidable in terms of column values, but if we can reduce that case as much as possible, then things will be much better. So my recommendation is that keep as many columns to not null as possible. And then, so you can limit your exposure to null weirdness. I know that's kind of standard advice, but it's the same thing as trying to make sure that we don't use null pointers when we don't have to in C or whatever. Trying to make sure that we keep nulls to the few cases where they're needed and where they're actually where they're actually going to simplify things is really, really helpful. If we can keep them away from anything that we might be querying and filtering on, that's much, much better. That may or may not be possible, but it's something we can strive towards. The second major best practice is to use nulls to filter out anti-joins like we do with this left join instance, right? And the reason for that is that's a much easier process for optimization than the exist query. And it's also quite clear in the sense that, if you have a convention to doing anti-joins in this way, you can always look at a join, you can go, okay, that's a left join, you can go, okay, that's an anti-join, right? And you can see it very quickly. And it's easy to reason about. The third major thing I would say is that you need to be pretty familiar with the different operators and how they handle nulls, because a lot of times operators may exist just for the purpose of null handling, like is not, is distinct from, is not distinct from. And if you're not paying attention to that, you may find yourself with unexpected problems. And then finally, the last point is don't try to understand nulls as a concept. They don't have a concept. They are simply an implementation detail, which is somewhat cancerous in that it has grown way beyond what it was initially used for. Sir Tony Hoare called null references his billion-dollar mistake. We took that from him, and we've probably made it a trillion-dollar mistake by now. So with that in mind, I would like to open this up to questions and answers. And I will check the QA section here, and we'll go from there. 1 second. Oh, I'm opening up the Q&A. Are there any other questions for example, about sort of hard corner cases and nulls and things like that. I guess one thing I would probably say at this point is that different databases, of course, store data differently. The way it works in Postgres is that the row header itself contains a bitmap which specifies which columns are null. And the not null check on the column only checks that bitmap. It does not evaluate the value itself. I would expect some similar behavior from most other databases, probably including MySQL and others, but I have not tested it, and this is an area where behavior is poorly defined enough that you can probably find some database that handles things differently. I'm not seeing any other. I'm not seeing any other questions. Are there any other questions at this point? All right. If there are no other questions at this point, I would like to mention that at Vettabase we offer health checks for databases. This includes trying to make sure that obvious performance problems, obvious health problems, obvious backup and similar problems, operational problems are looked at and addressed. I think usually it's much more on the performance side. So it's a great service we offer. I've done a couple of them. I think we do a great job on those. And so if you have a use for that, we'd love to help you out.